Okay, let's start. Thanks to the organizers for organizing this really nice workshop and for inviting me. And it seems like it's a great set of speakers and should be quite interesting the next 2 weeks. Today, I just want to sort of set up some of the stuff we might need in talking about high-dimensional expanders and so on. And today, I want to just talk about low-dimensional expanders, or what are just known as expanders. So just expander graphs. I'll cover a few different definitions of expansion and maybe talk a little bit about how to work with them and maybe how to use them for some properties. I should say, if you don't like these lectures, there are actually much better sources available. So let me tell you some references to look up. There's some very detailed ones on expanders, and there are multiple courses, including a classic monograph by Huri, Lineal, and Vigdorson. There is kind of in-progress book by Dan Spielman on algebraic and spectral graph theory, which is very nice, has some really nice kind of constructions of expanders, analysis, and also more general properties. There is a set of notes by Luca Trevisan from 2014, I think. I mean, there's a few iterations. And there's also actually a recent course on kind of low and high-dimensional expanders by Max and Shachar Lovet. 21, I think. Okay, so there are more details in these references. Please do look them up if you'd like to learn more about some of these topics. Just a kind of quick poll: how many people kind of know eigenvalues and eigenvectors for a matrix? Okay. Most people seem to know that. That's good. So yeah, I'll use some of that. But also, if you, please feel free to interrupt me, or kind of if I mention something which maybe you have seen in a different way, just stop me and ask me. It doesn't matter if I cover everything or not. We'll just make Max do it tomorrow. So yeah, just please stop me at any point. All right. So to start with, let's think of a graph, which is just a bunch of vertices and edges. We'll think of graphs as having n vertices. And for starters, we'll work with d-regular graphs. Okay? So the degree of every vertex is d. And we'll think of the parameter n as large, growing, going to infinity, d as a fixed constant. Okay? I mean, it'll be a constant which is not growing of n. I mean, it will not be an absolute constant like 3 or something. We'll need to keep it as a possibly large constant. Okay? And there are a few different notions of what it means to define kind of a graph is expanding and so on. And they kind of try to capture how well connected a graph is. And one notion, which is called edge expansion. So let's first define it for a set. So let's say I have a subset of vertices, and I define the expansion of this set as the number of edges that, let's call it phi of s. It's the number of edges that cross from S to S complement divided by the total number of edges incident on all vertices in the set S. Okay? So every vertex in set S has degree d. So this is the total number of edges which are incident on any vertex. And these are the number. This is just my notation for edges which cross from S to S complement. Okay? So if I have some set here, this is just measuring how well connected it is to the rest of the graph. Okay? And the expansion of the graph is defined as, okay, let's start with this. The minimum of this over all subsets S. Is this an okay definition? Sorry? shouldn't include everything, right? It's because then there is nothing left in S complement. Yeah. So in fact, in sort of, even it should not be very large sets because then this denominator is really unfair. I mean, if I have 90% of the vertices in S, then there's not much room for them to go in 10% of the remaining ones. So let's say if we have S and S complement, we'll always pick the smaller one as S and the larger one as S complement, okay? And then define this. Okay? This is what I'll call the expansion of a graph, or more precisely the edge expansion of a graph, okay? The minimum over all sets. And this, again, as I said, this is defined as the fraction of the total number of edges which cross. So it's a number which is, well, it's a fraction, so it's between 0 and 1. Can it be 0? Sorry? If it's disconnected, yes. So I can have a graph which has two parts, and I can take this as S and S complement if I have two connected components. And this, because it's not connected, all the edges are either here or here. Can it be 1? Sorry? Yeah, so that's a more kind of, so this quantity can be 1. This one, no, okay. So good, just sanity checks. There will be some set which you can find which will have some edges contained within it, right? So you can't always have that all edges in all sets go out. Okay, but let's focus on the 0 part of it. So we said it's 0 if the graph is disconnected, and it's actually trying to define kind of a robust version of connectivity. That not only is the graph connected, but there is some significant fraction of edges. Not only is there a one edge which crosses between any two pieces of the graph, but some significant fraction. And we'll talk over the next few days about connections to coding theory, but intuitively, if you think of the edges of the graph as carrying some kind of helpful information, and if you think of this blue set S as things where there are some errors or some faults occurred, right? What this definition is saying is that you kind of have friends who can help you. So there is some information which is available, which can capture sort of for any kind of corruptions, there is some information available from the rest of the graph, which you can use to fix the errors. Okay? And that's intuitively why it's used to design codes. And of course, we'll see more formal versions of these. Okay, okay, there's one more interpretation of this quantity which I want to maybe keep, and then we'll come back to it later. It's the probability that if I kind of take a random edge it's the same definition, it's not different. It's just saying that if I take a random edge starting from a vertex in S, then it escapes S. Okay? So it's also if you think of some kind of diffusion process in graph in which maybe you have some information, it's kind of spreading, it's just saying that it's for any set, there is no bottleneck, it kind of spreads very fast. Okay? And then we can come back to that. This is one notion. It's kind of useful for proofs, but there are issues with using this for algorithms because of this kind of so it's a minimum over all sets. The number of sets is very large, and kind of it's not always very easy to calculate this kind of a quantity or go over all sets and so on. So there is a different notion which we'll use, which is also algorithmically more tractable and kind of more convenient to use also for a lot of proofs. And that is what we'll use more, which will also generalize to high-dimensional expansion. And let's call that spectral expansion. Okay. So to go there, maybe let me mention one piece of notation which I'll use. So I kind of said U, V is an edge. Here, I used U, V as an ordered tuple, but it's an undirected graph. So you can think of either ordering on this tuple. So you can really think of it as either the unordered tuple, or for a lot of cases where I will write this expression, the order will matter, and we can just think of taking both orderings of every edge. You also think of u, comma v, and v, comma u. Okay, going back to spectral expansion. So let's, maybe make our way through this combinatorial definition in a slightly different way. So let's think of 1 minus the expansion. And let's write down what we have in a slightly linear algebraic way, and then we manipulate it a bit. Here we said this is equal to the number of edges. This time the number of edges that stay within S, because we are looking at 1 minus the expansion, divided by the total number. Right? So this was the number of edges escaping, this is the number of edges staying. And there is a nice linear algebraic way to calculate the number of edges between any two subsets in a graph using what is called the adjacency matrix of a graph. So the adjacency matrix has just entries if and only if the corresponding tuple is an edge. And we'll actually also used a normalized version of the adjacency matrix. So let's use A bar for 1 over D times the adjacency matrix of a graph. This is a notation we'll come back. And I'll write things more in terms of this A bar rather than A. All right, so let's write this expression. So, okay, the number of edges between S to itself, I can think of as a vector which is 1 on all elements of S, transpose, times A, times a vector which is 1, divided by D times this vector is just 1 in the positions corresponding to vertices in S. The vector transpose times this is just the number of vertices in S, and this counts the number of edges going from S to S. Everyone okay with that? All right. And now let's write it in terms of the expression we have. So let's absorb this D here. And okay. Okay, and this kind of expressions, so here we are writing down this expression which is taking the quadratic form of some vector with this matrix divided by just the length of that vector. These kind of expressions have a name in general, and they are kind of related to the eigenvalues of a matrix. So let's maybe define what this is. This is so for any symmetric matrix M, and we'll generalize this in a bit. And for any, let's say, function f, which let's say this matrix is in n cross n, and this function, this is just an n vector. The Rayleigh quotient of this matrix, this f, is just defined as that kind of an expression. It's just the quadratic form divided by the length of the vector. And it's also known that if you have a matrix which is symmetric, then it has eigenvalues which are real numbers, and in particular, the matrix as a whole can be written in a nice form in terms of its eigenvectors. So let's see. So for any such symmetric matrix, I can write it down as lambda I, let's say fi transpose where numbers I go from 1 to n. Lambda i's are real numbers. These fi's are vectors in Rn, and they are orthogonal to each other. And also, let's say length 1. Is everyone comfortable with this statement or not? I mean, we can certainly go into details of this if you want. Yes, this is basically what I need about eigenvalues or eigenvectors. Okay. So it's a nice way of looking at a matrix. Instead of looking at what a matrix looks like, what the numbers in it are, we kind of think of it as in terms of what it does. So when you look at it as a linear combination of terms like this, each term, fi transpose, is just something very simple. What this does, in terms of when you multiply it with some other vector, let's say g, you just get the dot product of fi and g, and you just get fi times that number. So all it does to any vector g is just kind of scale it by give you a scaled copy of fi, where the scaling is precisely the dot product. And the maximum of these kind of, and you can define also the eigenvalues precisely in terms of these relay quotients. But before we go there, let me say that I've been writing dot products in terms of this transpose and so on. More generally, this also works when you have some other notion of what I'll now call inner product between vectors. So it doesn't have to, and in particular, it will be more convenient even for regular graphs and certainly for more general graphs to kind of think of the inner product between two functions as expectation over v, f of v, g of v, where for now v is just chosen uniformly as one of the vertices. So let's be. So right now it seems kind of boring. I'm just taking the same thing, just scaling it or dividing it by n. But this turns out to be very convenient when we are dealing with graphs which are not deregular, where we have kind of varying degrees. Then we have to look at other kinds of sort of probability distributions for this expectation. And in particular, when we'll see high dimensional expanders, it is kind of necessary to use these or necessary to deal with graphs which are not necessarily regular. So okay, so maybe I'll, with some notational overhead, I'll use this notion of inner product between f and g. And actually, everything I said about these symmetric matrices is also true more generally, except that they have to be symmetric with respect to whatever that inner product is. And that just means that and this is true for our adjacency matrix. So okay, so a little bit of a detour, but we have ways of writing down eigenvalues and eigenvectors in general for for any matrix which satisfies this kind of a property. It's sometimes called self-adjoint. And the relay quotients are actually related to this expression by nothing but kind of, if you arrange the eigenvalues which are real numbers on the real line, then they tell you what the relay quotients look like. So in particular, you can define the eigenvalues. So let's say we have this matrix. We write down its eigenvalues, lambda 1, lambda 2, let's say in some descending order. And then it is true that lambda 1 is is equal to max, or maybe correctly speaking supremum, but let's say max, of F, which is non-zero. And let's say the corresponding eigenvector, let's say, is F1, then we can define lambda 2 as doing the same operation, but now this time we are searching over vectors which are orthogonal to the first eigenvector, because we kind of said they form an orthonormal basis for the whole space. We found the maximum, now we want to kind of just look at the rest of the space, so just sort of look at the directions orthogonal to it. So and so on. This seems okay. It's based on what you know about symmetric matrices or eigenvalues. Yes? Okay. That's basically all I need from linear algebra. And now we are actually ready to define spectral expansion. So let's do that. Okay, let me erase this part. So there are actually two ways, or two definitions, depending on how strong you need the spectral expansion to be. But let's look at this matrix A bar. Let's write down its eigenvalue lambda 1, lambda 2. Okay. I claim for the way we defined it, the matrix, lambda 1 is easy to calculate. 1, why? I'm sorry? For A, D is an eigenvalue. Why? So, okay, good. So lambda 1 is equal to 1. And if you take in particular the all ones eigenvector, so D times this. And so if you, because if you think of what this matrix does, it just averages the value. So at the vertex corresponding to U, the entry here is just an average of the values at all the neighbors of U. And everybody has a value 1, so the average is 1. This is preserved. Okay. Why is this at most 1? So this shows that there is a vector with eigenvalue 1. Why is that the maximum? All the eigenvalues lie between minus D and D for the adjacency matrix. Okay, so formally speaking, we need a proof of that. But yeah, I mean, for any symmetric matrix or for any matrix, you can bound the eigenvalues by the sum of the absolute values of entries in a row if you want. There is another way to see this, which is kind of to define the Laplacian, which is identity minus this, and because you just took identity minus a bar, its eigenvalues will be 1 minus lambda 1, and so on, 1 minus lambda n. And saying that this is equal to 1 is the same as saying as this is equal to 0, and it's also kind of a nice exercise to prove that this is at least 0. In fact, let me kind of assign exercises for the tutorial. So it's kind of a nice way to interpret what A does and what L does. So if you think of the inner product of F, A bar, and G, it's the same as looking at a random edge And now you think of both orderings. And for the Laplacian, let me just define the symmetric version. It's easier. It's okay. So this is an exercise, but if you believe this statement, then it's clear that this quadratic form is always greater than or equal to 0. So all eigenvalues which are defined in terms of some Rayleigh quotients are always greater than or equal to 0. And so equivalently, this is always less than or equal to 1. Okay. So the first eigenvalue is 1. And now we just define spectral expansion in terms of what happens to the next eigenvalue. So one-sided spectral expansion is just kind of defined as how much is the gap between 1 versus the next eigenvalue. And a lot of the times, it's more convenient to work with the two-sided version, which is so you arrange the eigenvalues. You kind of, if you are looking at the largest eigenvalue in absolute value, that also is 1 by the argument you were saying in terms of row sum. And you kind of say, okay, if you are looking at the second largest in absolute value, it can either be this one, or it can happen that this one is negative, but it's really, really negative. And again, it's a good exercise to check that if lambda 2 is equal to 1, then your graph is disconnected. If lambda n is equal to -1, then your graph is bipartite. So, and this again captures some sort of robust versions of these statements. This graph is kind of robustly connected, and this is saying it's kind of robustly connected and somewhat robustly far from bipartite. Any questions? All right. So we defined this other notion, which was sort of motivated by looking at expansion and kind of changing from Rayleigh quotients over indicator subsets to Rayleigh quotients over arbitrary functions. And there are a couple of inequalities which actually relate these two notions, and we'll talk about one of them briefly and the other one in a bit more detail. But the first one is Cheeger's inequality. And this one says that the eigenvalues or the spectral expansion, even the one-sided spectral expansion, is both an upper and lower bound on the edge expansion of a graph. So if you have some reasonable lower bound, let's say 0.1 here, then the edge expansion is already pretty good. It's at least whatever, 0.1 divided by 2. And on the other hand, if your graph has some good edge expansion, then it must also have good spectral expansion. So these two notions are related up to this kind of quadratic loss. And this is useful in certain regime of parameters when maybe you're dealing with somewhat moderate kind of expansion. In applications to codes and pseudo-randomness, we will work with, often we will be able to kind of use a much stronger form of spectral expansion when this quantity will be very close to 1. And then you can get actually even better expansion guarantees in terms of edge expansion, and then we'll get to that in a minute. Okay. But let me just kind of quickly prove at least half of this inequality just to make sure we all understand the notation and parts of it. Okay. So the easy side of Cheeger's inequality, which is what is often proved in courses, is this part, which is to say that if you have a graph so one way of reading this is that if your edge expansion is small, so if there is some set which only has a small number of edges going from S to S complement, then the second eigenvalue is also smaller. It's kind of, it is also large. It's close to 1. So our goal is to, and remember we defined the second eigenvalue as the maximum over all F, which were kind of orthogonal to the top eigenvector, and we now know that the top eigenvector is the all ones eigenvector. So it's just F inner product all ones is equal to 0. F is non-zero. Of this expression. So the proof of this is just to exhibit such an F. We want to show that lambda 2 is large, it's very close to 1. So we just want to show one F for which it is large, and then we are done. Any suggestions? So, and we have a set S which witnesses small edge expansion in the graph. So any suggestions on how to produce an eigenvector or this, not even an eigenvector, just a vector? Okay, so I should say, one power of this notion of Rayleigh quotients is it kind of reduces algebra to optimization. So eigenvector definition is very algebraic. You want to say something is an eigenvector if you have m times f is equal to lambda f. This A is a very precise notion. You have to have equality everywhere. You have to, so it's also slightly brittle. This is a kind of surprising connection that you can actually state an algebraic quantity as a solution to an optimization problem. And now it becomes much nicer because you just have to understand the search space for the optimization problem, just prove bounds on that search space. A lot of the time it can be done by just exhibiting one point in the search space, which is what we are going to do. So, I mean, this connection between Rayleigh quotients and eigenvalues is kind of relatively simple, but quite powerful because it lets us connect algebra and optimization. All right, going back. Any suggestions on how to construct such an F, how to exhibit a solution for this? Sorry? Indicator of S, okay, that's, so the suggestion is F as the indicator of S. Does it satisfy all the conditions we need? Good, okay, so we are trying to work out this. Does it now satisfy everything we need? But yeah, we're getting warmer, so yeah. All right, so it's certainly not 0. Half of the things are satisfied. But what we want is the inner product with all ones or the expectation of the entries. And I mean, so this is kind of, so you filled up some entries which are ones basically in the place where S is. Don't leave the other entries 0, just fill them up with negatives and just kind of calculate the right one. And once you come up with this vector, it's a simple exercise to check that it will give you this kind of a bound on the second eigenvalue. So you will get lambda 2 is sufficiently large or sufficiently close to 1 so that 1 minus lambda 2 is small. Okay, but I just wanted to emphasize this translation between subsets and indicator vectors, which can be thought of as these linear algebraic objects or these functions. All right. Any questions? So let me kind of mention the next version of, or like the next inequality, which we'll use more often when dealing with codes. Which is called the expander mixing lemma. And in fact, I'll state something a bit more general, but let's say expander mixing lemma. And if you only remember one thing from this lecture, please remember this statement. This is something which will be very useful when dealing with codes. So what is the expander mixing lemma? It kind of requires a bit stronger guarantee on lambda, on this eigenvalue. And in fact, let's define a piece of notation for this maximum, like the second largest eigenvalue in absolute value. So let's say lambda is equal to the maximum of lambda 2 and the absolute value of lambda n. And the expander mixing lemma says that for any subsets S and T, the number of edges between S and T is close to this number, P over N times size of S times size of T. We'll interpret this number in a minute. Minus up to a small error term, where the error term we should think of as small when lambda is small. By the way, I should say, I've been using kind of these definitions of expansion. We kind of said, let's say we work with a version where lambda is really small. I haven't told you that these graphs exist. Okay, and maybe if I sort of just prove a lot of properties and it turns out that no graph exists with lambda less than 0.1, then maybe you'll not talk to me for the rest of the week. So we do know how to construct these graphs, and for any arbitrarily small constant lambda, as long as it's independent of D, we know how to do this, and even random graphs will do it, and I'll talk more about constructions towards the end, and also what are the kind of bounds we can hope for lambda. But for now, think of lambda as any small constant, 1 over 100, as long as it doesn't depend on D, we are fine. Okay? Questions? Okay, is the statement at least just what it's trying to say? Okay, yeah. Okay, so we're just trying to calculate the second largest eigenvalue in absolute value, right? So it can happen that lambda 2 is also on the other side of origin, maybe, I don't know, right? But let's say we had 1 and then we had 0. Let's say in the extreme case, lambda 2 was here, but then lambda is here, lambda n, right? Because it's even smaller. So in absolute value, lambda n will still be larger than lambda 2. So the second largest eigenvalue in absolute value will be either lambda 2 if it's on this side of the origin, or lambda, or whatever is the absolute value of lambda n. And it can also happen that lambda n is also on this side of the origin, but then its absolute value will be smaller than lambda 2. So these two quantities suffice. Yeah, maybe they're not both always necessary. Other questions? Okay, and let me also kind of write down a statement of this in terms of these inner products or functions and so on, which will be useful. So, so let's think of, and then we'll prove that one. So let's think of functions f and g, which are functions from vertices to this, or you can equivalently think of them as vectors in Rn. Then the quadratic form f a bar g minus inner product of F with 1 and the inner product of G with 1 is less than equal to lambda times the L2 norm of F, okay. Let's clarify what this means. Norm of G, where the norm of F for any inner product, we can just define as the inner product of F with itself, square root, and this is the inner product of G with itself. Okay. Not necessarily. So right now, there are arbitrary subsets of the vertices. Good. Thank you. So the way we will so we need to more precisely define what this quantity is when there is an intersection. Let's say we just consider all ordered pairs and think of edges where the first vertex is in S, the second vertex is in T. So yes, I'll include the edge ones if they have intersection. But this is a more precisely defined version. And you can think of this as whatever you will get when you plug in F as the indicator of S, G as the indicator of T. So I've also told you how to maybe go from this statement to this statement, which, do you have a question? Oh, no. Okay. Other questions? Okay. So we'll prove this, but okay, let's maybe see a proof, and then I want to give you some interpretations of it. But let me just mention that this quantity is what you would expect if you had a random graph and you picked one vertex from S, one vertex from T, and the edge was included with probability D over N. So if you were including every edge with probability D over N independently at random, this is the expected number of edges you will see going from S to T. And in this sense, it's saying that the number of edges is roughly what you would expect in a random graph up to a small error. So one interpretation of this statement is that the expanders behave like random graphs with respect to at least tests which count edges. If you have a test which just says, here is an S, here is a T, does it look like a random graph? Yes, it does, up to this error, which is the variance term. Okay, and we'll come back to interpretations of this, but let's prove maybe this version. And as maybe you already said, you can deduce this version from this one by just plugging in F as the indicator of S and G as the indicator of T. Okay, so we said any symmetric matrix, in particular A bar, has a decomposition in terms of its eigenvalues and eigenvectors. Let's call the eigenvectors Fi's. Okay. So now I have to be a little careful, because if I write the decomposition this way, I have a bit of a problem, because if I multiply it with any function G, I will get Fi transpose G, which is not quite how I defined the inner product of Fi and G. So one way to deal with it in this particular case is that the inner product of Fi divided by G is just 1 over n times Fi transpose G. So I could divide this term by n and divide this term by n to correctly scale things. Then it will have the property that I was trying to say, that for any matrix M, I can think of it as summation lambda I times its eigenvectors if they were Wi, Wi. And then if I multiplied U, then it had this very simple action. When you did this, you got the component along Wi was just scaled. The component along Wi will just scale by lambda I. But now the component along Fi is really the inner product of Fi and G, if we are thinking of this space as defining a different inner product. And so that inner product has this factor of n off. And there is a more general piece of notation which I'll introduce because it will be useful when dealing with more complicated notions of inner products. You can also think of this as, I mean, it's really Fi transpose, just written in a fancy notation. There's this notation of outer products. And you think of G as also a vector like this. So a vector is just written this way. And this is just a simple matrix, which when you multiply it with G, all you get is these two combined to become an inner product. So you get the inner product of Fi times G. Times Fi, right? So it's what we were trying to do, the component of G along Fi times Fi. But this works for any inner product. It just hides this scaling notation and sometimes a bit more complicated inner product. It can be just hidden away as this part of this notation. If you don't like it for now, just think of dividing by n. But this fancy notation is just Fi divided by n. But, or maybe root n. Yeah. Oh, thank you. Yeah, I can either write it for a bar or this. So now let's just maybe look at what the second statement is, and then and let's calculate what we get by just writing this decomposition for a bar. And if Fi's are the eigenvectors of a bar, then what you will get by kind of multiplying F from one side and G from the other is, everyone okay with this, just the first step? I mean, again, if you think of here, you will look at F transpose times Fi, that will be one inner product, Fi transpose times G, that will be one inner product. And I'm just doing this more generally for whatever inner product we have. And we know one of these terms. We know lambda 1 is 1. So let's just take it to this side. And let's write down the rest of the terms. And we want to, let's say, understand the absolute value of this. Then it's less than equal to the absolute value of this times the absolute values of all the terms here. Everyone okay so far? And now we do know what is the second largest eigenvalue in absolute value, or we have some bound on it, right? We called it lambda. So this absolute value of lambda I for all i's between 2 and n is at most lambda. And the rest of the term, okay, we have a product of two kinds of things. In one way to handle it is Cauchy-Schwarz, so let's just do that. So it's less than equal to lambda times, let's apply Cauchy-Schwarz. And now, these FIs or the eigenvectors were an orthonormal basis for the space on which in which F and G live, right? There are an orthonormal basis for the space on which the matrix A bar kind of acts. So I'm just summing up the square lengths of the components along all the basis elements, maybe all but one. Okay? And this is just Pythagoras theorem. This is just the length of or the inner product of F with itself because these are orthonormal basis elements. So this is less than equal to lambda times norm of F times norm of G. Is everyone okay? So, right. The proof seems fine? So, yes? No? All right. So, as I said, this is a very simple lemma, but it's also surprisingly useful, and I want to give at least 3 different interpretations of this before we break. And I mean, in some sense, all my coding theory papers over the last 3 years have been just expander mixing lemma. So let me at least tell you some interpretations of this. So the first one, which we already saw, is that if you count the number of edges between S and T, then you get roughly what you would expect in a random graph. Okay. Another way of putting this is expanders are pseudo-random. Okay. They're pseudo-random in the sense that if you have tests which check or count the number of edges, they behave like random graphs. Another interpretation which kind of just comes from the second statement that we wrote down and the exercise I assigned. So we can think of F A bar G as picking a random edge and calculating the product of F of U times G of U. And the second term, which is just the expectation of like the inner product of F with 1, which is just the expectation of F, because we defined this inner product using just expectations. And since I have 2 expectations, I can write them as picking U a random vertex, picking an independent random vertex V, and looking at F of U times G of V. And then this is less than equal to lambda times whatever the bounds is. And so think of this term as kind of checking the correlation between U and V, or trying to measure this product using the edges of the complete graph. So you pick edges of the complete graph just means you pick a random U and independent random V. Let's say complete graph itself loops. And this expression is very close to what you would get by just looking at the edges of an expander. So you don't really need to look at the edges of the complete graph or equivalently the product distribution on U and V. And so another way of putting this is that expanders sparsify the complete graph in some way. And it turns out when we look at high-dimensional expanders, they are hypergraphs. If you pick a random hypergraph, that's not quite what we want from high-dimensional expanders, but sparsifying a complete hypergraph is a much better definition for a high-dimensional expander. And then Max will probably make this more precise tomorrow. Okay. The third interpretation of this, which is actually even for a special case of this that I want to maybe write down. So let me actually take G to be A bar times F itself, or I mean, that you can prove even without applying this particular conclusion just from the proof of the lemma. But we can get the following statement. Let's see which version I want. Okay, so for a function f, let's think of a function f prime, which is f minus expectation of f in all coordinates. So it's just a constant function, so that for f prime, the expectation is 0. All I've done is subtracted the component along the all ones vector, right? So it's and when you apply the expander mixing lemma, or even just a second eigenvalue bound to expand for expanders to this version, what you get is so you can think of this as maybe this as G. And this is nothing but actually, yeah, if you kind of work out both the left and right hand sides, you will get this version, which you can also derive more simply, but yeah. This is just saying that f prime is orthogonal to the all ones vector. We have just subtracted that component. And in all the other directions, the length shrinks by at least a factor of lambda, just because that's the second eigenvalue. But this version has a nice interpretation, which is the following. So, let me write down. So now let's write down what are the entries of this a bar f prime. Okay. As I said, a bar, all it does is, so first of all, our inner product is an expectation measure over U. And we are going to look at a bar f prime U whole squared. Okay. That's the left-hand side. Another way of writing, and now what is a bar f prime? It just averages the value over all neighbors of U. So this n of U is just my notation for neighbors of U. And it averages the value of f prime. What is the value of f prime? Well, the value of f minus E of f. And what we just claimed is that this is less than equal to lambda square times the norm of f prime, or maybe the norm of this vector. And now let's for a second think of this term as just 1. So the norm of f is 1. This is saying, if you look at the local average, so if you look at f, just calculate its average on the neighbors of U. Typically, it's very close to the global average. Okay? And so it's like a Chebyshev-like inequality. So this is expectation. And if I want to write down what is the probability that the average of f over the neighbors minus the global expectation of f is larger than delta, then this is less than equal to lambda square divided by delta square times whatever that was. So for any function, the local average just over neighbors looks very close to the global average. And in some sense, this is the reason expanders are very good at local to global phenomena. So we use expanders for taking small codes with some nice local properties and then getting big codes with nice properties. We use them to get metric spaces with nice properties. This is, in some sense, why? Because this is a global statistic, some global property of this function f, and it looks kind of for every neighborhood, the local picture of that statistic looks like the global property. And if we have some nice guarantees on how local pictures look inside an expander, we will also derive a guarantee over global pictures because typically they are close. And maybe show a quick example of this after the break. But this is just another consequence of expander mixing lemma and one of the key reasons driving kind of a lot of the local to global phenomena that we get from expanders. Okay. So Yeah, let's meet maybe in half an hour and we can continue. Any questions, by the way? Sorry. Okay. So sparsifying, yes, thank you. I should have clarified. But I just meant the number of edges in an expander. I'm thinking of as n times d divided by 2, which is if d is small, it's much less than the number of edges in a complete graph. So just in that sense, just this distribution has fewer points in its support than this distribution. Other questions? Okay, let's meet in half an hour.